Cool. Yeah, great. Thanks a lot. Thanks for the invitation and thanks everyone for coming. So most of what I'm going to talk about today is the sort of the subject of this recent preprint together with Luca Battistella and Drew Ranganathan. But this is sort of part of a wider circle of ideas. So at various points, I'll kind of circle back to these earlier papers as well. So I'm going to be talking about two Gromov-Witten theories. So let me sort of briefly introduce those and tell you how I think about them. So the setup is sort of our target geometry. We've got a smooth projective variety, and then we've got an SNC divisor. Okay, so so X is a smooth variety, D is a divisor, and it has smooth components D1 through DK, and they're intersecting transversely. Okay, so et al. Locally, it just looks like a bunch of hyperplanes intersecting in affine space. In such a situation, what we want to consider is sort of stable maps to X, but we want to impose tangency orders along D at the mark points. Okay, so with tangencies. And so how does this work? So sort of when you're setting up the data for your problem, right? So you have this discrete data like the genus and the curve class and the number of markings, and you have this extra bit of data, which is the tangency orders. Okay, so these are some numbers C, I, J. So this would be the tangency to, okay, which way around have I done it? Okay, DI at the point PJ. Okay, and the idea is you want to study stable maps, which in some sense have these tangency orders at the mark points. And the question is, how do you model this? How do you model this problem? So the starting point is something that I'm going to call the nice locus. So what this is you look at maps from a smooth source curve. Okay, and you just impose the tangency that you expect. Okay, so how do we write this down somehow in symbols? So if I pull back the equation for the ith divisor, then I expect this to be the product of equations to the markings with the appropriate exponent. Okay, so this is the product, let's say from j equals 1 up to n. Okay, so this is sort of the open locus in some sense that we want to compactify. Okay, so of course, as usual, right, this equality is going to be just up to units. And really, if you want to be careful about it, of course, what's really going on, sorry, so this is for all I, sorry. So this is for each sort of component separately, this should be the case. And of course, what's really going on is that there's sort of an isomorphism of line bundles, which is, identifying the sections. What do I want to write here? Cij. PJ. Okay, so so this is this is the kind of moduli space that we're interested in, but of course this thing is not compact, right? So well, first of all, I assume the source curve is smooth. It could break. That's not such a big deal, but more importantly, as we degenerate into the boundary, C could fall inside some of the divisors, right? So when that happens, what this this thing on the left hand side is just going to become the zero section. And at that point, it's slightly unclear, how you talk about it being tangent. I mean, you could say it's tangent to infinite order, but it turns out that if you just add in all those objects, you don't really get a well-defined theory. Okay, so there's some question about how to compactify this. So of course, we want to compactify because we want to do enumerative geometry. We want something we can do intersection theory on. So there's various answers to this question. I'm going to focus on two today, and I'll be talking about how they're related. So these two are the roots and the logs, or the orbifolds and the logs. And in both cases, the idea is to add some extra structure to the source and the target. Okay, so to my curve and to my x, and then we're going to require the map F to respect this structure. Okay, and the question is simply which extra structure should we add? So one approach leads to this theory of log stable maps. And so in this case, you attach something called a log structure. Okay, so I'm not going to tell you exactly what this is, but I'm going to tell you how you should think about it. So you should think of a log structure on a scheme as being some collection of functions on the scheme, which you declare to be monomial functions. Okay, so this is some collection of monomial functions, and in some sense, putting a log structure on a scheme is sort of choosing some functions and declaring I want these to be monomial. Okay, and these functions behave like monomials. So for example, you can't sum, well, you can sum two monomials, but you won't get a monomial. So that's sort of out, but you can take their product, right? So if you take the product of two monomials, you'll get a monomial. And so the sort of algebraic structure that monomials form are semigroups, okay, or monoids, the things that go into the construction of toric varieties, okay? And so this is why you often get this phrase sheaf of monoids, but all it really means is a sheaf of functions, which I'm going to think about as monomials, okay? So in the context of these tangency, this tangency problem, the relevant monomials will be the equations defining the divisor components on the target and the equations defining the markings on the source, okay? And something will also happen when the curve becomes nodal, but I don't want to talk about that right now, okay? And you can see, right, that this, this identification here is it's sort of exhibiting f as a monomial function, right? So it's the type of toric morphisms, for example, that you'll see in toric geometry. And that's basically saying that this is going to respect these structures. But the sort of beautiful thing is that, or I guess the helpful thing is that, this equality somehow imposing that the map F is a logarithmic morphism means that you have a notion of this equality even when geometrically your curve is mapped inside the divisor. So even when your curve is mapped inside the divisor, where this basically just becomes zero, there's nevertheless some map of sheaves sort of in addition to the scheme theoretic map, which is recording this isomorphism. So it lets you make sense of that, okay? And so this leads to a compact moduli space whose deformation theory you understand, and so on and so on, and you get a system of invariants that come out of this. The second theory is the theory of orbifold stable maps. This is a theory developed by Abramovich, Graeber, and Vistoli, which makes sense for any smooth Deligne-Mumford stack. But in our context, what we do is we construct something called a root stack. So starting with a smooth pair, starting with an SNC pair XD, you construct a smooth Deligne-Mumford stack, which I don't know, maybe is written with fancy X. The idea is this is something whose coarse moduli space is just X, so it's not actually changing the underlying scheme, but we're introducing some Jerby structure. We're introducing roots of the divisors, so we're introducing some Jerby structure along the divisors, and similarly on the source curve we'll be introducing Jerby structure along the markings. Okay. And in this case, in this context, the tangency order is encoded in the homomorphism of isotropy groups. Okay, so the isotropy groups will always be cyclic groups. Finite, it depends how you set it up. But anyway, there'll be finite abelian groups, and the tangency is encoded in the homomorphism of isotropy.
So can I ask you a philosophical question? Do you view these two definitions, do you view them about the same complexity or a different complexity?
I'll say, so yeah, what do you mean by complexity? Yeah.
You have to choose however you want to understand this question.
I think I'm going to answer this question in two different ways during the talk. So if it's okay, I'll just flag when I answer it when I come to it. Okay, great. So in any case, there are these two definitions and they both lead to theories. And maybe the thing to say is that, in both cases, the addition of this extra structure turns this tangency condition into a deformation open condition in the appropriate category. Okay, so here you work in this category of log maps. And if you're looking at schematic maps, this tangency condition is a closed condition, and that makes the deformation theory very hard to understand. But when you're in this log setting, this condition is satisfied in families, or continues to hold in families, and so somehow this becomes deformation open. And similarly for the orbifold theory. Okay, so let me say a couple more things about these. So these both lead to moduli spaces, and maybe just the first thing to point out, just to sort of make us not too freaked out. Both of these things are finite over their image in the space of ordinary maps. Okay, so you've added this extra structure, but this is quite different to the expanded theory where you can really have, a lot, when you're looking at relative maps with expansions, you can really have a lot of stuff that gets collapsed in M bar X. This doesn't happen here. So both of these things really are finite. And in many cases, you really can just think of them in terms of their image. Okay, so, of course, legally you can't do this, but in practice, it's quite useful to have this point of view, at least for sort of formulating, statements and counterexamples.
Hey, Navid, is there some virtual sense in which that finite map is a normalization? Like this kind of thing happens.
Yeah.
What I mean? What I'm asking.
Yeah, I mean, I think that's basically right. So so there's this issue there's this issue called saturation. So the fact that it's not, the reason that it's not one-to-one is to do with this condition that the log structure on the base is saturated. And so I think the basic answer is yes, but somehow it's never been entirely clear to me how, like, that's my intuition, but I've never actually proved this, and I haven't, it's never been clear to me how it's sort of written down. But for example,
well, or it's not even clear how to ask that question correctly, I think, probably, right?
Yeah, but like, okay, so for example, if you look at, like, in fact, this kind of brings me on to the next thing. So if you look at like Pn rel H, then, for example, Gartman has a definition of a moduli space, which is like literally take the closure, right, of the thing. And I think in that case, we can actually prove that this is a normalization.
That's in genus 0.
Yeah, in genus 0. That's right. Yeah. Yeah, that's right. So one should expect that this is a normalization of the image. Yeah, absolutely. Thanks. Are there other questions? Okay, great. So okay, so they're both finite over their image in maps. And okay, I guess this is what kind of related to what I was saying. So if we look at sort of simple examples like PR rel H, or the universal smooth geometry, which, yeah, okay, I mentioned later, they both contain this nice locus as a dense open. Okay, so they're sort of faithful compactifications in some sense. Okay, so that's for the similarities. What about the differences? This is sort of related to Rahul's question. So these things have very different flavors. The logarithmic theory, okay, maybe I'll start with the Orbifold theory. The Orbifold theory is much closer in spirit to classical Gromov-Witten theory. So you have access to, things like WDVV, torus localization, boundary recursion, things like this, the standard corpus of techniques that you have, degeneration formula, the standard corpus techniques that you have in ordinary Gromov-Witten theory. In the log theory, you have access to some of these techniques, but really the much stronger connection is to tropical geometry and tropical curve counting. So these tropical correspondence theorems that relate log invariance to tropical curve counts play a much more fundamental role. So these are things that, work, for example, very well for toric varieties, and then the generalizations into non-toric settings, you end up going into this world of scattering diagrams where you try to calculate these things. So they have very different flavors, and probably, I guess what I'm really saying is they have very different techniques. Okay, so
but I don't know if that's exactly right, in the sense that the log space has all the things we have in Gromov-Witten theory, but it's all the log promotion. Most of it hasn't been studied enough. Like instead of having relations in regular Chow ring of MGN bar, you need to have relations in log Chow. And the degeneration formula has some kind of log promotion, and localization has a log promotion. Just that we're not very good at it.
Yeah, okay, sure. Maybe this is like, as of the state of the art, we don't have access to these techniques. Yeah. I guess part of the point of this talk and some of this work is to try to get some of the techniques over to the other side, or at least to get some understanding of like what there's all these in principle statements, right, which say that okay, if you blow up enough, then you can relate these two. But we're, as you say, like we still don't fully understand, for example, like in some situations, do we have to blow up that much? Maybe we don't have to blow up at all. There's various kind of questions that are unanswered here, and this is one way to kind of approach this. Yeah, I think we're agreeing. But anyway, okay, so so the goal is to try to compare this for the most part, to try to kind of import the techniques that we have on the Orbifold side into the log side. So so let me talk about the results. So we want to compare the log and the Orbifold theories. Okay, so here's a theorem from sort of 5 to 10 years ago, due to Abramovich, Cadman and Wise. Okay, and the theorem says that if I work in genus 0, and crucially, if I assume that my divisor is smooth, okay, then the invariants just coincide on the nose. Okay, so the log theory equals the Orbifold theory. So this is a very satisfying, satisfying result, and it's useful for various things. So we want to try and extend this, and there's two.
But the Orbifold theory has a parameter, the R and the root stack. You're saying this is so you want to say for any something like that.
So for me, the Orbifold theory is always the R tends to infinity limit. Yeah, that's right. Okay, so there's two directions in which you can generalize this. And we sort of can break it down as working in higher genus and working with SNC divisors, right? So my D had these components, and I want to assume that K. I really want to assume that K is at least 2. Okay, so you can think of this as kind of making the source more complicated, and you can think of the other one as making the target more complicated. Okay. Okay, and so a lot of work has been done, especially on the left-hand side. So I'll say, for example, the Yanda Panda Panda Pixton's Vonkin proof of Pixton's formula can, in some sense, be viewed as a log to orbifold correspondence. You have this rubber theory, which is in some sense a log theory, and Pixton's formula has this, again, parameter, and somehow what you're doing is extracting the term of this parameter, which coincides. You're extracting the piece of the orbifold theory that coincides with the log theory. Okay, so this is some form of this, and then relatedly, so Tseng and Yu combine this approach with the degeneration formula to prove actually pretty much this result that I've stated, but in higher genus. So again, in this case, the statement is that the orbifold theory is it no longer stabilizes as the parameter goes to infinity, but it becomes polynomial in the parameter, and the constant term equals the log theory. Okay, so this is sort of the left-hand side of this. We're going to focus on the right-hand side. Okay, so for us, I'm going to work always in genus 0, but I'm going to assume that really my divisor is not smooth. Okay, the thinking being that, and I hope to convince you by the end of this that there's quite a lot of stuff that happens on the right-hand side already in genus 0. And so somehow it's sensible to do this before sort of trying to recombine them later on. There's some conjectures here, but we don't yet know how to prove them. But if you'll see, I mean, for those of you, and I think there's a lot of you in the audience who are familiar with the story for the double ramification cycle, what you'll see is that the genus 0 version of this story is actually very similar to the higher genus version, the higher genus story for the the story of the double ramification cycle, which is higher genus. So in some sense, you see higher genus phenomena even in genus 0. But anyway, we'll come to that. Okay, so from now on, we're going to be in this setting. So the genus is going to be 0, and I'm going to have at least two components of my divisor. And so the first, I'm not sure whether to call this a theorem or not, but anyway, the first sort of observation due to myself and Dhruv is that the log theory is sort of not the same as the orbifold theory. Okay, so there's an explicit counterexample, and the counterexample happens pretty much as soon as you would expect. So it happens for P2 relative 2 lines and degree 2 maps. Okay, so more or less the first example you would think of. They're different. And maybe another way to think of the difference between these two, maybe this question of which one is simpler, is that the log theory is more enumerative. Okay, so I will present this counterexample in some detail, and we'll see why the log theory really, in some senses, is more enumerative than the orbifold theory. Okay, so this is kind of a negative result. So now I'd like to present a positive result. So just firstly, for some background, so there's this result of Dan and Jonathan, which says that the log invariants, okay, so these invariants of XD are unchanged under strata blowups of D. Okay, so I have X and I have D, I get some stratification of the boundary, and if I blow up strata, then the invariants don't change when I do this. Okay, so this is referred to as the birational invariance of the log Gromov-Witten theory. By the way, this shouldn't be super surprising. I mean, the theorem is not easy to prove, but the statement kind of makes sense. If you're counting curves in X with tangents along D, then in some sense, you're counting curves in the complement with some sort of prescribed asymptotics as you go to infinity, right? It's sort of like, what's the difference between a toric variety and an algebraic torus? Well, not that much, right? It's somehow, a toric variety is like a torus that sort of knows where one parameter subgroups are going to end up as you go towards infinity, okay? And a similar thing is happening here. So you should think of somehow the torus as being this complement, okay? So it sort of makes sense that if you were to blow up the boundary, you're not changing the interior, and you should expect the counts not to change. Of course, this is not literally true. You can't blow up any point on the boundary. You really have to blow up strata. And the reason for that is because you need to maintain control of the asymptotics as you're going to infinity. So if you start arbitrarily blowing up strata, you won't be able to control the asymptotics. But if you do strata blowups, then you're fine. Okay, so
But this theorem is about the virtual class, right? Not about just invariant, just the numbers.
Yeah, that's right. So it says that okay, I'll just write it. So there's a map from, there's a map like this, and it preserves the virtual classes. Yeah, that's right. So, okay, so I suppose, of course, the invariants you need to consider. I mean, all your insertions have to come from the base, because otherwise, yeah, yeah.
And maybe I can ask you, if you go back to if you go back to this diagram with the genus 0. So this, the Tseng Yu, is that also about the virtual? I don't remember now. Is that also at the level of the virtual class, push forward to?
Yeah, I think so. I mean, it's proved via the degeneration formula.
And so it should be fine. And your side, if you, I mean, genus 0, there's not much M0, but if you keep all the markings, you could keep them. So you can also prove that at the level.
Yeah, everything we do is also at the level of the virtual class. Yeah, absolutely. Yeah, thanks. Yeah, okay, so there's this fact. So if you sort of blow up X, and you take this is the strict transform of all the divisors plus all the exceptional divisors that you end up with. This defines some new pair, and there's a map like this which preserves the virtual classes. Okay, so somehow the theorem, the sort of main theorem that I want to talk about today. So this is together with Luca and Druve. So in a sentence, it says that this birational invariance is the key property that distinguishes the log theory from the orbifold theory. Okay, so let me just write it down. So if we fix our discrete data, okay, then what we get is an iterated strata blow up, which we can describe fairly explicitly in terms of tropicalizations. So as an iterated strata blow up, maybe I'll call it, like this, satisfying two conditions, okay? So firstly, if I look at the orbifold theory of this blow up, so the orbifold theory of X dagger D dagger will be different from the orbifold theory of XD, okay? So it will change as I've done this blow up. It does not satisfy this birational invariance, but nevertheless, once I've done a finite number of blow ups, this is now stable under further blow ups, okay? So now this is birationally invariant. Okay, so you think of this as some kind of limiting orbifold theory for the strata blobs. Okay, and then I guess the main point of the theorem is that once you've done this, then the orbifold and the log theories coincide. Okay, so the orbifold theory of this blow up will equal the log theory of the blow up, which by Abramovich wise is the log theory of the original pair that you started with. Okay.
Sorry, and is this again only for classes coming from XD, or is everything agree once you do these blobs? Excuse me. So this comparison doesn't know about X. So this comparison is for any classes coming from X dagger. Yeah. But I mean, of course, if you want to compare it to XD, then you would want your classes to be pulled back from XD. Did I answer your question? Maybe I misunderstood the question. No, that's great. Thank you.
Okay. Great.
And this theorem is for genus 0, but the Abramovich bias is for all genus.
That's right. Yeah. So maybe I'll just say what the conjecture is for higher genus. So the conjecture for higher genus is basically that everything is the same, except that down here you have to extract the constant term of this orbifold theory will still be polynomial in the routing parameters, and you have to extract the constant term. That's the conjecture, but it's not straightforward to there's some issues that I can talk about at the end maybe.
So blowing up doesn't make the divisor any less singular, but it is the point that if you've got conditions, you can start to pull the components on which those conditions are on apart. How does blowing up help? That's what I'm trying to figure
roughly speaking. So I mean, I'll talk about this in a bit more detail later, but yeah, roughly speaking, you can't quite, so what you would like to do is blow up and force kind of transversality of everything. So you would like to say, okay, once I blow up enough, my curve only intersects the codimension 1 strata. It doesn't intersect the higher codimension strata. But this is just not true. You can't do this. No matter how many times you blow up, you're always going to intersect the higher codimension strata. But somehow you can bound you can essentially constrain the complexity of in our language, constrain the complexity of the types of tropical curves that will appear. So for example, I'll just give you an example. So once you blow up enough, you can never have a situation where you have a curve in the interior intersecting, intersecting the intersection of two divisors. It has to first go into one divisor and then go into somehow the next divisor. So there's various kind of combinatorial constraints you can, impose, which allow you to prove the result, basically. Yeah. Yeah, thanks. Other questions?
So in this higher genus, but you're saying there's some polynomiality, but that's only in the kind of orbifold parameter. It's not like there's a polynomiality as you blow up farther and farther.
No. Yeah, I mean, once you've performed this initial blow up, we haven't proved this, right? The conjecture is that well, actually, no, sorry. I mean, this is always polynomial in the routing parameters. So somehow, yeah. But so I will discuss the proof strategy a bit, and I think at that point it will maybe become clearer why why this is a conjecture, and somehow why you might expect this to be true. Yeah. But I mean, the way to think about this in a word is that this thing here, excuse me, the orbifold theory is some sort of limit orbifold theory. Okay, so it's sort of the limit under all the blowups. Okay. And so what you do is you replace the orbifold theory of XD by this limit theory. The limit theory satisfies birational invariance basically by construction. And then somehow the theorem is that once you impose birational invariance, then the theories coincide. So birational invariance was the only thing stopping them from coinciding. And I should say, this is kind of, this limit orbifold theory business is sort of, even in, you see this to a certain extent, even in the smooth divisor case. So for smooth divisors, you have to take R going to infinity. And somehow, for smooth divisors, the only log modifications that you have are these Kummer extensions, like ramified covers, basically. So that's the R goes to infinity thing. But once you have more than one divisor, you also have these blowups, and somehow there is a sort of uniform, structure going on here, but from the smooth to the SNC case. Yeah. Cool. Questions? Okay, great. So I'll just state a sort of one corollary that we deduced from this in the paper, which is some sort of reconstruction result. So it basically says that the log theory of the pair can be reconstructed, algorithmically from the absolute theories of all the strata. Okay, so XD. Theories of all the strata. Okay, and you prove this by pushing everything over to the orbifold side. And then I kind of like this result because it uses a bunch of facts that various people have proved. So for example, it uses facts about the Gromov-Witten theory of projective bundles, of ordinary Gromov-Witten theory of projective bundles, of blowups, of gerbs, and various other things. So this is, this is some version of the topological view, or at least one of the results in the topological view paper, but for SNC devices. Okay. So it takes me about halfway. So for the rest, I'm going to sort of tell you, basically, I'm going to work up towards the counterexample and then sort of give you an idea of how the proof goes. Are there questions before I start?
So this corollary would be true also in higher genus if you had proven that conjecture.
Is that true? Yeah, this should be true. Needs to be a bit careful. I mean, I don't remember if all these results we use are like proved in higher genus. I guess, okay. So
I think basically on the Gromov-Witten side, everything's in higher genus. But,
yeah. Projective bundles, gerbs, blow up. Yeah, I think you're right. Yeah. I think everything we use, there's some, at least sort of, I mean, this is a kind of soft statement, right? It's like can be reconstructed. So at this level, I think it's known. Yeah, Shenhua says yes. Okay, great. Great, cool. Other questions? Okay, so I'm going to talk. I'm just going to introduce this sort of strategy that we use. So the idea is the following. So we have this SNC divisor, and what we want to do is we want to bootstrap. We basically want to bootstrap from the smooth divisor case. Okay, so we want to bootstrap result from the sort of known case. Whoops, of smooth pairs. Right, so meaning, I have my, all right, sorry, let me just write it down. So I have my SNC divisor, and so I have a bunch of smooth pairs, right? K of them, in fact. And I know that the theorem holds for the smooth pairs, so I would like to just, be really lazy and use that to deduce the theorem for the SNC pair, okay? Okay, so So let's just see how this works. So I'm going to set k equals 2 from
Sorry,
now
sorry.
on.
Which theorem are you proving now? The first
sorry.
one.
So, well, okay. I guess I'm gonna, yeah, well, both actually. So, I mean, I want to address the question of how can I compare log and orbifold? So I'm going to do that by trying to reduce the comparison to the smooth divisor comparison where everything is known. Yeah. So, so I'm just going to work in the case of 2 divisors. You see almost everything here. There's a couple of phenomena that aren't visible here, but almost everything is visible at this level. And it's just going to make my notation sort of less painful. And so the first sort of observation or theorem, which first appeared in this paper with Lucas, Shenhua, and Fanglong under some assumptions, and then like genus 0 and convex, and then in this recent paper we removed all these assumptions. Is that the orbifold theory satisfies a product rule sort of relative to the space of maps to X. Okay, so the orbifold theory okay, so what do I mean by that? So I will just draw some diagrams. So I have this orbifold space with these 2 divisors. And then over here, I'm going to form this fiber product. So I have the orbifold space with respect to D1, going just, finite morphism down to maps to X, the orbifold space with respect to D2. I just form the fiber product. Okay, and the theorem says that, firstly, this thing gets a virtual class in a natural way. And moreover, this map preserves the virtual classes. Okay, so this is some version of the product formula that everyone is sort of happy with, except you replace the space of stable curves with the space of stable maps to X. Okay.
But this is also a limit result, or it's true at every finite level?
No, this is always.
That's what.
Yeah. So I think for the next kind of 20 minutes, there won't be any blowups. So I'm gonna put the blowups in back at the end. But for now, I'm just gonna focus on X rel D1.
No, I wasn't talking about blowup. I was talking about the R parameter.
Oh, I see. Yes, I mean, yeah. I mean, in fact, this isn't even really anything sort of that special about root stacks, to be honest. But yeah, that's right. So, well, okay. I mean, why am I saying that? I mean, you need something to fiber over, but somehow, there's not that much. This is not a super difficult result to prove. Somehow, it follows roughly the same pattern as the proof of the product formula over MGM bar. Yeah. So you should think of this F as being basically an intersection. Okay, so these things are finite onto their image, and I'm basically just taking the intersection. Okay, so one way to think about this is that I get the orbifold space for the smooth divisors by just intersecting the 2 orbifold spaces. Sorry, I get the orbifold space for the SNC divisor by just intersecting the 2 orbifold spaces. Okay, so that's the way to think about this. And the sort of the corollary of this is a relation amongst the virtual classes. So let me write it down, and then I'll take the complaints after. So it's that the virtual classes satisfy a product decomposition. Okay, so I can write the virtual class for X rel D1 plus D2 as a product like this. Okay, so of course, and this is happening really in M bar X. Okay. Okay, so of course the complaint is that this product doesn't really make sense. So it does make sense, for example, if you assume that X is convex, in which case, this thing is smooth and I have intersection products. But yes, you're right. In general, it doesn't make sense. But nevertheless, there's some version of this you can do, for example, for the universal target and so on. But anyway, I don't want to go too much into that. But I think this is sort of a good principle to just have in mind. Okay, so why is this useful? Well, of course, I know from the smooth divisor comparison result, the Abramovich-Cadman Y's, that these 2 factors give me the 2 log classes. Okay, and so the natural question arises: does the log theory satisfy a product rule over M bar X? Okay, so does the log theory satisfy the same product rule? And if the answer was just yes, then I probably wouldn't be here today because, well, I mean, I'd probably be here, but I wouldn't, be alive, but I wouldn't necessarily be giving this talk because, I mean, you'd have a nice comparison result, but you would just sort of put, this equals log, and then you'd sort of be done. But as you probably guessed by now, the answer is no. Okay, so it doesn't satisfy a product rule, at least not a corrected product rule. So there are corrections that one needs to introduce, and these add a lot of complexity to the problem. Okay, so as has already been alluded to, there's a similar story here for the double ramification cycle. So you can consider the sort of higher rank version of the double ramification cycle, and this does not satisfy a product rule. But it does after you blow up the moduli space enough. Okay, so after you blow up MGM bar and you pass the transverse classes, then the transverse intersection, on the blowups will give you the right thing. And of course, the same thing is true here. So you could pursue that line of reasoning of like blowing up the moduli space. So sort of in a similar vein, you could blow up M bar X and try to transversalize the intersection this way. And so this is, for example, what Dhruv and I do in this earlier paper on maximal contacts. So this is sort of blowing up the moduli space, but what we're doing is really blowing up the target. Okay, and in some sense, it is in some sense sort of different, fundamentally different. You're in particular, for example, your moduli space is sort of changing, and you're sort of replacing your intersection problem with a different intersection problem rather than just sort of transversalizing things. So yeah, there's that sort of tension. Okay. So let me show you why this is. Let me show you how this happens and what goes wrong. So so first a definition. So this first appeared sort of in an early form in my thesis, and then sort of developed in this paper with Dhruv. So this is this thing we call the naive space. So the naive space is just the fiber product. So I take, okay, let's start over here. So I have my log space with respect to D1. I have my log space with respect to D2. I both map them to M bar X, and then I just take their fiber product. Again, you can think of this as an intersection. It's, it is profitable to think of it that way. Okay, so so this is a thing that, in a perfect world, this would just be the same as the log space with respect to D1 and D2, but it turns out it's not. Okay, so let me just point something out though. So the fact that log equals orb for smooth divisors, okay, combined with this product rule, this implies that so this naive space has a virtual class, and you can define invariants, and it implies that the naive invariants equal the orbifold invariants always. So meaning without any blowing up. Okay, so this equality always holds. Okay, and so consequently, you can sort of for the purposes of comparing the orbifold to the log theory, the question becomes, how does the naive theory relate to the log theory? Okay, so does log equal naive? Okay, so this is somehow the way that we like to rephrase the question, because this is something we can work with more concretely. Okay, so with that set up, now I can talk about the counterexample. Okay, so maybe I'll just pause for questions. Okay, so before we get comparing these, I just want to point out a few facts. So often, where often will be specified in a moment, this log space is very well behaved. Okay, so it's irreducible, of the correct dimension, and it contains this nice locus as a dense open. Okay. So it contains this nice, maybe nice and naive look kind of similar, but anyway, sorry about that. This is the thing I defined right at the beginning. So it defines this nice locus as a dense open. Okay, so for those of you who know what this means, the log space will be log smooth. Okay.
So Navid, can I ask a question?
Yeah, sure.
So you said there's no log product formula, but there's this paper by Leo Hare called the log product formula.
Yeah.
And I guess, sorry, I'm just very naive. So like you said that there's some correction times. His thing looks very natural, but I guess the point is that, so like, what's wrong with it?
Yeah, there's nothing wrong with it. So the problem is, okay, let's.
I think he blows up everything, right? I mean, that's the.
Yeah. So okay, this is like bad book work. Bad board work. So this is not a definition of the naive space anymore. I'm just using the diagram again. So you can consider this diagram. Okay, and this diagram does exist, and it's Cartesian, but it's only Cartesian in this FS category. It's category of FS log schemes. Okay,
and which comes down to blowing up and
yeah, that's right. So you can make them coincide. If either of these two maps is like combinatorially flat, then the Fourier products coincide. Yeah, so I mean, my understanding is, what Leo does is he defines a Giesen pullback for these FS categories, but I think when you unravel it, it amounts to performing this blow up and then well, I mean, that's one way to access what this refined pullback is, basically. Yeah.
Awesome. Thank you.
Yeah. Yeah. So okay, so where were we? Yes. Okay. So
by the way, I would say I personally would object to the statement that this is often the case. I think that's a peculiar use of the word often, but anyway.
Yeah, that's okay. I mean, so what do I mean by often? So yeah, so let's say like projective space relative to some reasonable number of hyperplanes, or perhaps more importantly, an Artin-Fan. Okay, so the universal. So I mean, this is kind of the fun thing. So projective space relative to a hyperplane, you can view this as the universe. Okay, so let's start over here. So AREL-D is the universal geometry, right? This is the universal smooth pair. In some sense, not in some sense, you can view PRREL-H as the universal, the universal ample geometry, right? So you can bleep that out afterwards, right? Yeah, so
that's way above our pay grade. We don't know.
Yeah.
Sorry, it's stuck in there now.
That's okay. So I mean, the point is, the fact that it's true for the universal geometry is helpful. I mean, this is how Abramovich and Cadman and Wise prove the log Orbifold statement for smooth divisors, right? They prove birationality on the level of the universal geometry, which they do by relating it to this nice locus, right? By finding a dense open in both. So yeah, I think this is a reasonable approach to this problem. Okay, but anyway, so the point is that this log space is for these nice targets, it's well behaved, but maybe the counterpoint I'm trying to make is that this naive space is almost never irreducible. So even for these very simple targets, and you can think of this naive space as being the geometry of it is very similar to the geometry of the Orbifold space. So their components will be basically the same, and so this gives you some sort of way of accessing this. Okay, so it's almost never irreducible. And it has excess components, and these excess components will contribute to the invariance. Okay, so that's why the invariants are different. Okay, so what you should imagine is that I have my log space, and it's living inside my naive space, and I should think of this as something like the inclusion of the main component, or maybe to be slightly more precise, it's a sort of log desingularization of the main component. Okay, so this is very analogous to this whole genus 1 story with the reduced invariance. Yeah. Okay. So yeah, I guess another way to say the same thing is that this log space is something like maybe I won't say this. I mean, okay, I'll just say it, but I won't write it. So this log space is the closure of an intersection. So I intersect my two nice loci. I get a nice locus, and then I take the closure. Whereas the right-hand side is an intersection of closures. So I take the closures first and then I intersect them. And that's why this really is a strict inclusion, because there's non-transverse intersections happening when I pass to the boundary. Okay, so let's do an example. So here's the example I've been promising. So my pair is P2 rel 2 lines, and I'm going to work with degree 2 curves. And I'm going to just fix one marking. I don't know, let's call it P1 with tangent C, which is tangent to sort of both curves simultaneously. Okay, both divisor components. So tangent C 2, 2. Okay. So let's just do a quick dimension count, right? So I'm studying conics. So there's a 5-dimensional space of conics. I'm imposing tangency to 2 lines. So that takes off 2. But it's more than that, right? I'm imposing tangency to 2 lines at the same point. Okay, so it's really -1. So this problem has, this moduli problem has virtual dimension 2. And so here's just a fact, which is that this geometry, P2 rel L1 plus L2, this is convex. Okay, and so consequently the moduli space is everything nice I just said about it. So it's irreducible. In particular, it's irreducible and 2-dimensional. Okay, and it's the closure of the locus of maps from smooth curves. Let me just close my email. Okay. Okay, so that's for the log space. What about the naive space? So I'm going to identify an excess locus. So I'm going to look at stable maps to P2 of the following form. So the source curve has 3 components, C1, C2, and C0.
So can you,
Yep.
I don't see any nice curves like this.
Yeah. I mean, nice is I guess subjective. Yes. So you're right. So all the curves will have to be double lines, but they're still maps from smooth curves, which are not contained in the divisor. So from the point of view of log geometry, the log structure on the base of the log curve will be trivial. So this is sort of the locus where the log structure is trivial. So from our point of view, they are nice, but yes, I agree. In some sense, they're not that nice.
I mean, they're double covers of lines that go through that point that are ramified at that point, right?
That's right.
At the intersection point.
That's right. And so the closure of that locus will be this log. That log space will contain that locus as a dense open. Okay, so now I'm going to identify some locus in the naive space. So here's my, okay, so my source curve is in blue, my target is in black. So I'm just going to map. Okay, let's just do it. So, okay, so C1 is mapping with degree 1 onto a line. C2 is mapping with degree 2 onto another line, and they're meeting at the, at the intersection point and connecting them as a bridge containing the marking. Okay, so C0 is contracted to the intersection of the 2 lines. Okay, so it's easy to check that this lifts. So if I view this just as a map to P2 relative L1, then I can lift this to an expansion of the target. Okay, just P2 relative L1, and I expand, get the P1 bundle over L1. It's easy to see that this lifts to an expansion on that side. And it's also, just by symmetry, it lifts to an expansion on L2. Okay, so this is in the intersection of the images of the log spaces. Okay, so this defines a locus in the naive space just because I have a lift to both of the rank 1, the smooth divisor expansions. Okay, but of course the observation is that this locus has dimension 2, the choice of the 2 lines. Okay, and so the observation here, the conclusion here is that this naive space has 2 components. Okay, so it looks something like this. So this is my naive space. So one component is the main component, which is this log, and the other component is this excess component that we've just identified. Okay, and they meet somewhere. We'll say a little bit about how they meet in a moment. But in this context, I keep saying, I said that the naive space has a virtual class, and that there's a way to define it. But in this context, it really is just like the intersection product. Okay, when I take an intersection, and whenever you're in a situation where your intersection has several components of the correct, all of the same dimension, this is just going to be some weighted sum of the classes. So in this case, it turns out the multiplicity is 1. Okay, and so the class of the naive space is given by this sum. Okay, and in particular, the invariants are different. Okay, so remember, this is giving me the same. This is giving me the orbifold invariance, and so the difference is sort of contained by intersections against the excess class. Okay, and so one can find. I mean, I think on general grounds, one can always find insertions that will intersect with this non-negative, non-trivially. But in this paper with Drew, we write down. We actually do this calculation, so we write down some explicit, choice of insertions.
Can you do this example in degree 3 somehow? Yeah. I mean, you can imagine also with the 2-2, there's a cusp. There's some kind of. You can't do that here with the cusp because it's not enough degree for a cusp.
So do you want to have 3 lines, or you want to have a conic and a line?
But basically, this is going to fail in every case.
Yeah, that's right. I mean, it gets worse. So, for example, if you did it with 3 lines, you'll now have excess dimension 1. In the excess dimension is going to be the number of lines minus 2.
Yeah, I see. But this place is good because you don't. If you put a 2-2 and 3, you get a cusp, I guess. But this case is good because you don't have to do any virtual class analysis with this expected dimension.
Yeah, that's right. It's just a sort of intersection multiplicity sort of calculation. Yeah, that's right. I mean, I should say, so of course, we find some insertions which pair to 0 with this. Of course, I'm not saying that all the invariants are going to be different, right? So, if you choose your insertions well, they may well pair to 0 against the correction term. And there are cases like if you look at, for example, Shenhua and Fenglong's papers, there are cases where the invariants are known to coincide if you choose your insertions correctly enough. But it's just in general they'll be different because you'll pair non-zero against this excess class. Yeah, thanks. Okay, so let's come back to this picture. So, if I choose some random point in this excess locus, it doesn't admit a log lift, okay? It only admits a log lift if it belongs to this intersection. So how do we make sense of this? How can we sort of see this geometrically? So there's kind of two ways. So the first way is to consider the geometry of the expansion. So what we do is we start with our P2. So this is our P2, and I'm going to degenerate to the normal cone of the intersection, okay? So we get some picture in the central fiber that looks like this. So this is my exceptional. I've now blown this up, and there's some point to infinity that I'll label for future use. So I have my map down to P2, and I'm asking whether it admits a log lift. Okay, so there exists a lift to this log space, right? So P2 L1 plus L2. So this happens sort of if and only if there's a predeformable lift to this expansion. Okay. Okay, so the picture we're after is something like this. Right, let's do this again. So here's my degeneration to the normal cone. And so, okay, let me just draw it. So, previously C naught was contracted into the intersection, but now it's going to become a conic in P2. Okay. And so here this is f of C1 and f of C2. Okay, so this is just basically the strict transform of the lines that I had before blowing up. Okay, and I'm asking for this map from C0 into this P2, which will have the correct tangencies here. Well, I mean, in this case, it's just transverse contact. Okay. Okay, but now here's the observation. This is basically what Tom noted, right? So C0 is a conic in P2, which is tangent to both of the branches at x infinity. Okay, because this is where the marking is here, right? So the marking has gone off to infinity. It's where I was imposing tangency. So it's tangent to both branches at this point to infinity. Okay, and consequently, this, C0 has to be a double line, right? There's basically more precisely, a double cover of a line. There's no other choice. Okay, and a consequence of that, if you look at this picture, right? So I had these 2 points here, and what was I calling them? Let's say f of Q2 and f of Q1, the images of the joining nodes on the source curve, right? And so the consequence of this is that these points have to be the same point on E. Okay, there's no choice. I have a line in P2, it's intersecting E in 1 point, and I just have 2 points mapping down to that. And so, the consequence of that, if you look at what's happening at level 0, is that these two had to be the same line to begin with, right? So f of C1 and f of C2, these lines that I started with before blowing up, they had to be the same line. Okay. Okay. So if we go back to this picture here, where are we here? So this locus was just the moduli for the two lines, and this red thing is basically the diagonal inside this moduli. It's saying that the two lines had to be the same. Okay. Okay. Why am I telling you this? The reason I'm telling you this is I sort of want you to see why blowing up helps. Okay, so all right, so I was going to say something on excess loci, but I'll skip that. So let's come back to this positive result now. So you can see here that if I blow up, okay, so all right, let's perform this blow up. So I have L1, L2. Now I replace it by this blow up. Now, what's happened, right, is that so previously, right, I had these two lines going into the corner and I had a contracted component going into the corner, okay? Now I'm still going to have a contracted component somewhere on the exceptional, but of course now in order for everything to glue together, these two lines had better be the same line, or rather the strict transform of the same line downstairs, okay? And so basically what's happened is that the gluing that we needed for the expansion is already imposed on the level of the collapse space, okay? The gluing is already imposed in the naive space. Whoops, excuse me. Gluing. Okay, and consequently what's happened is that this excess locus has disappeared. Okay, so the excess component has disappeared, and so now naive invariance and the log invariance coincide. Yeah.
But when you blow up, you change the conditions, right? Somehow they were tangent, now it's just passing.
Yeah, that's right. So there's a way to lift the tangency conditions. So I can actually, I can explain this. So so before blowing up, right, I had this. This was my tropicalization, and I can impose the tangency condition at the marking by just putting a vector there, right? When you blow up, so the blow up is actually introducing this ray, right? So you go from having 2 tangency with respect to the lines to having just tangency 2 with respect to the exceptional and tangency 0 with respect to the strict transforms. Yeah, this is just some way of formally, in some sense, you're formally computing the strict transform of the curve that you started with.
So I mean, if you blow up enough, then you're always just, it always goes to tendency 1 or whatever, 0 or 1.
Well, it wouldn't be 1, right? So this was 2 before. So this still has tangency 2 along the exceptional.
Oh.
Right. It's just it always goes to this disjoint case where every marking is just tangent to a single component of the divisor. Yeah.
Mm-hmm.
But actually, it turns out that that's not enough. You know, to get the right blow up, that's actually not quite enough. And I'll actually say a little bit about how we know when we've blown up enough, basically. So I guess I just drew this, but redraw it. So this blow up here corresponds to this subdivision. Okay, so these now correspond to the I've got the geometric picture here and the sort of fan theoretic picture here. And the way to think about what's happened here is we've introduced a ray whose slope was basically the slope of an edge in a tropical curve. Okay, so in this previous example that I had, maybe I'll just draw it. So this thing that was causing the excess locus, there was a tropical curve, or a tropical map really, which looked something like this. Okay, so these 2 vertices correspond to the external components, and this one corresponds to the internal component. And it was this edge here which had slope 1, 1. Okay, and so what you have to do is you have to introduce the slope of that edge as a ray in the target. Okay, and the blow up that you sort of want. So now I can be a bit more specific about this theorem. So it's not just some abstract blow up. So what you do is you write down all the possible, you fix your discrete data, you get some finite number of tropical combinatorial types of tropical curves that can appear, and you just enumerate all the slopes that appear along all the edges in those curves. Okay, and once you've done that, you introduce all of those as rays, and then that's enough. So this is this condition that we refer to as slope sensitivity. So once these are introduced, you have enough rays to sort of conclude the theorem. Okay, yeah, so I'm more or less out of time, so but that's okay because I'm on the last page as well. So so the proof, okay, so maybe I'll just say a tiny bit about the proof. So the proof is basically you construct a suitable expansion, okay, of your target.
But is there some way to describe this expansion more intrinsically, rather than this specific set of blowups?
The blow up, you mean?
Yeah. Yes, sorry, that's the blow up, yes.
So it's any blow up which includes all of these directions as rays. That's actually how we define it. It's more like a condition than iterated blow up, if you see what I mean.
But maybe there's a geometric object associated to the initial geometry which realizes all of this. What we find in the DR story is that you get this, if you pick a suitable stability condition, in that it'll provide for you enough blowups. It's a kind of more conceptual way to think about it.
Yeah.
Rather than listing the blowups in some explicit sense. I don't know. Maybe this is just something to think about.
Yeah. No, definitely. I mean, yeah. Sam was telling me about this. I guess I need to see the. I need to learn this.
It's not so clear the solution there is exactly your solution. Just the idea that there's you start with the original geometry, and there's something in that geometry, a moduli of something, or something that will realize it already knows how much to blow up.
Yeah, okay. No, I mean, this would be good. I mean, I guess the difference is that somehow, I think, I mean, correct me if I'm wrong, but I think what you guys are doing is blowing up the moduli space and then performing the sort of fiber product over the.
Yeah, you're blowing up the space itself. Yeah, I agree.
Yeah, so I mean, probably there is some, way to get back, but on the face of it, it's quite different, right? Because not only when you blow up, not only are you changing the X that you're intersecting in, you're also increasing the number of divisors, right? So every time you blow up, you get more divisors. Now you need to intersect more things than, like like here you were intersecting two things, but now you're intersecting three spaces because you also have this E that you're imposing tangency to. So it's a little bit of it's a slightly different approach to the problem, but I mean, it's still not entirely clear to me how the two approaches are related. I'm sure they are, but yeah. Yeah, thanks. Okay, so yeah, okay, so okay, I'll just wrap up now. So we construct an expansion. So this basically follows via sort of tropical geometry. There's some combinatorial arguments, and then one needs to construct a lift, a predeformable lift. Okay, and so this is sort of more, I guess, geometry, well, algebraic geometry, I guess. Okay.
But still, Navid, so in fact, the whole issue is about the product formula. I guess you said that,
That's
but
right.
that's what actually everything here is about, the product. Once you get that product to work, then you're golden.
That's right. That's right. So you sort of place the orbifold theory to the side. You know, you say, okay, I know the orbifold is the naive theory always. So I just place the orbifold theory to the side, and I just compare the sort of the refined product with the non-refined product, basically. So yeah.
But in genus 0, that first step is not exactly correct. I'm sorry, in higher genus, the first step is not exactly correct. It's not just about the product in the higher genus.
No, yes, sorry, yes, you're right. Yeah, you're right. So there's some, yeah, so that, in fact, okay, yeah, so maybe I can, so I was going to write this, but maybe I'll just say it.
But you have plenty of time, you know, you have, the seminar goes for 75 minutes, not 60.
Oh, does it? Okay.
Yes.
I had no idea. Okay, I planned okay, great. I planned a 60-minute talk. Okay, in that case, I can go back and say some things I was going to say. Okay, so okay, let's talk about higher genus since it's coming up. So so why can't we just do the same thing for higher genus? Okay, so it's not clear that we can't. So okay, I'll say two things. So the first thing none of you will care about, but you need to be a bit more careful with the tropical combinatorics. Meaning, I mean, the reason you don't care about it is because I haven't told you how the proof goes. Okay, but you need to be more careful in the combinatorial steps of the proof. So at various points in the proof, we use the fact, we're kind of lazy, right? So we just say, whatever, like the source curve, the graph is like a tree. So I can just like iterate along the tree and like construct things in this way. And of course, when you're in higher genus, you can't do that. So you need to be a little bit more careful, but I don't view this as an insurmountable problem. It's just something that requires a bit more work. But maybe the thing that's more important is you need, and this is why this kind of orbifold to naive is a bit tricky in higher genus, is you need or you want some version of the Seng-Yu comparison for sort of universal targets. Okay. Okay, and again, I'm not sure to what extent this is insurmountable, but there's various sort of technical things that show up here.
So what do you mean by this? You mean for this, the relative, I mean, what do you mean by this for relative universal targets?
Yeah, so I guess, so I guess what I mean is I have, so what's the right thing to say? Okay, so I have some log space of maps to A rel D, and I have, what am I saying? So I have, and I have an orbifold space of maps to A, which is this thing they call AR. So it's like the root stack of A, which is A, and you want some kind of, what we would like is some roof that compares the two. Okay. So in higher genus, like this, in genus 0, this is how ACW prove the comparison, right? They construct this roof and then they have a class here and they push it forward. But in higher genus, I mean, they don't prove it in higher genus, right? The Seng-Yu proof is different. It uses the degeneration formula somehow. So maybe one can get away from this by just diagram chasing enough. But honestly, I was sort of like exhausted from all the diagram chasing. So I think we sort of decided that, to be honest, this is really the statement that we want somehow. Okay, it should have to do, there's some. I mean, I think. I don't want to misattribute, but I think various other people have thought about this problem already. So there's various sort of ideas that go into this. But anyway, this is the thing that we're kind of missing at the moment, basically. I guess this is sort of, I guess, upcoming work to do. The other thing that is sort of upcoming, but I think I can say this is more work in preparation than work in progress. We basically know how to do this now, is a version of this for these negative contact invariants. Okay, so so this requires basically one key new idea, which is really inspired by this paper of Fan, Wu, and Yu. So so in this paper they relate the orbifold invariance with high age to a theory of invariance with negative contacts, which is defined in a slightly different way to the sort of ACGS punctured theory. Okay, so it's defined by this graph sum, but nevertheless, there's a relation and there's this class that's involved, and so we now have a sort of, I think, fairly conceptual understanding of this. It's in some sense it's a parallel result, because what we do is we relate the high age theory to the ACGS theory, but the structure of the result is very similar. Okay, so and so once one has this result, then pretty much everything that I've said will apply to give a version for negative contacts. And the reason you care about this is because you want to get access to things like the WDVV equations. So when you use the boundary splitting in the orbifold theory, you have to invert the band of the and you have some you're splitting at some node, but you're fibering over kind of the inertia stack, right? So you have to invert the ages of the node, and so this immediately takes you out of the world of sort of positive contact invariance, which is for small ages, and into this high age world, which is what these people study. So yeah. So anyway, so once one has access to this, then there's various applications that you can imagine developing. Okay. So there are questions.
So everything you said is about this simple normal crossings. If you take like P2 relative to a nodal cubic, then the orbifold theory has its own problems, but let's forget about the orbifold theory. But can you say something about this?
Yeah, I mean, I guess what we would do is, so we would first just blow up to get into the SNC case and then just argue from there, right? So so you can always do this. So yeah, so we would just blow up to get to SNC and then take that as our starting point and then go from there.
Yes.
Yeah, that's right. Yeah. Other questions?
Is there an idea that you can identify the correction terms between orbifold and log before blowing up somehow?
Yeah, so so one way, okay. So I would say, like, I mean, not clearly via this method, right? So I mean, the question basically results to comparing two orbifold theories, right? So the orbifold theory of the blow up versus the orbifold theory of what you started with, right? And at least I'm not sort of, I mean, people have worked on this, but it's not sort of entirely clear to me how, how to do this sort of in general. I don't know if anyone in the audience knows. I guess the other approach is this thing that we keep alluding to, which is to blow up the moduli space instead. So this would be like I mean, I can talk about this. I mean, this was in this, so like, for example, in this precursor paper with Dhruv in the maximal contact case, where you basically consider, yeah, okay, maybe I'll say this. So you consider this diagram, this sort of pre-fiber diagram that I keep writing down. Okay. And we've already said that the fiber product here is not going to agree with the log space, and the reason for that is that neither of these two maps is combinatorially flat. Okay, so there are cones here that are mapping non-surjectively to cones here, and let me just sort of spell out what those look like tropically, because I think the comparison with the DR is very compelling. So here's a cone in the relative space. Okay, so this is indexing a combinatorial type of tropical map, so R positive, right? And you can see, right, that there's a relation amongst the edge lengths, because essentially what's happened is the fact that you had a vertex. So in the rubber geometry, you're your target is just sort of like R with no vertex. So you never get a relation sort of somehow unless you have a loop in the graph, right? But here, because you have this vertex, this forces a relation between the edge lengths. So in some sense, this is very close to the genus 1 counterexample in the DR setting. It's basically, you know, the fact that you have this vertex here sort of forces you into this higher genus world. Anyway, so to answer your question, what you want to do is to run semi-stable reduction for this map. And I mean, in this paper, what we basically show is that if you restrict to this maximal contact case, where you just have a single marking with maximal contact, then the blow up you have to do here is very, very explicit. So it's an iterated blow up along strata with a specific ordering, or an iterated weighted blow up along strata. So in that sense, you get a formula in some sense. I mean, it's a sum over strata and iterated blow up. You use the blow up formula of Fulton's. Whether you can calculate with it beyond any small examples is sort of less clear. But yeah.
But I mean, I think that if you want, like in the case when you have just one divisor to calculate the other R terms, is that your question, Johannes? That the other terms of the polynomial in R?
No, not necessarily. I mean, it was really about about basically seeing this counter. I mean, in the counter example, you see explicitly there's one good component and one excess component. And probably you can identify what the contributions from the excess component are in that case. And so basically the idea is just how to generalize this.
Yeah, so I can say a little, I mean, we don't have a very good understanding of how to enumerate the excess components in general. So, I mean, in some sense, if you have the iterated blow-up description, you don't have to, because you somehow write it as a sum. But maybe I'll just say one thing. So, the excess components all arise from bad intersections of boundary strata, right? So you have a boundary stratum here, a boundary stratum here, and you're mapping to some boundary stratum. And so, these are indexed by, I mean, we can just do the counter example that I wrote down. It looks like this. So I have a boundary stratum here mapping to, so please tell me if the picture is not, I don't know how familiar people are with this language. So, so these are corresponding to cones in the tropicalization. So there's some cones sigma 1 here, some cones sigma 2 here, and some cone tau here. And the excess dimension, you can just work out, just sort of by a dimension count, what the excess dimension of the fiber product. So this is, my excess component is living up here, right? And you can just work out what the excess dimension is. And I always get the sign wrong. I think, did I write it down? Okay, up to sign, it's always excess dimension versus excess codimension. Let's see, is that right? Yes, okay, excellent, that's right. So, in some sense, you can at least enumerate excess strata in this way, just by counting the dimensions. And there's an approach using the extended tropicalization. Actually, Sam, are you here? Is he still here?
Yeah, I'm here.
Did you guys put this in the paper in the end? I know you've talked to me about this.
No, it was going to be an appendix, but it never survives. Okay,
all right. Well, okay. Sorry to maybe sorry if you were keeping this as a surprise, but anyway, there's this theory of extended tropicalizations can allow you to enumerate the excess components. But I mean, in principle, meaning if you have complete information on the cone complexes, then you could do this. Yeah. But yeah, like I say, I mean, the complexity grows very quickly, so it's unclear what one can say, for sort of computational purposes. But anyway.
So if I can make a comment, I don't think that's the hard part, but you did say something about semi-stable reduction, and then using a blow-up formula.
Yeah, that's right.
I think this is not so. I don't think that's so easy, because even if you can do the semi-stable reduction, your blowups are not the ones that allow you to use Fulton's formula. Then you have to make some choice. You have to filter your blowup.
No. So okay, hold on. So in the maximal contact setting, so when I say blowup, I don't mean like arbitrary subdivision. I really mean like there's a list of strata in like boundary strata in M bar X, and there's an ordering on them, and you blow them up one by one in this ordering. So
so you have complete control over the blow-up.
That's right. So Fulton's blow-up formula really does apply. Yeah. Okay, technically it's the weighted version of his blow-up formula, but whatever, you can do this.
So is this special to genus 0 or?
Yeah. It's special to everything. Yeah, it's special to genus 0, and it's special to this maximal contact. It really is special to this maximal contact. The fact that you have one marking with tangency. As soon as you have more than one, this doesn't work.
So can you put the? Oh, sorry. Are you finished?
Yeah.
No.
Yeah.
So can you put the statement of that topological view theorem in genus 0?
Sure.
There's something confused about something confused me about it, but now I think that's at the beginning almost. You say the genus 0 log theory is reconstructed from all strata. So all the complete intersection strata of the. But where does that come up in the argument? So this statement is also true when you don't have simple normal crossings, as you just explained.
That's right.
But where does it come? Where do you get the intersection of D1 and D2? And
where do you need all the strata? Yeah. So basically, you. Okay. Let's remember how this goes. Okay. So the first. It's like a long step, but basically the point is that at a certain point you get. So what you do. So there's this trick that that like Fanlong and Shenhua use, where you put X inside a projective bundle. And you sort of you basically you reduce the sort of theory of X to the what's the word? Yeah, you reduce the theory. You put X as a complete intersection in some projective bundle, and then you reduce the theory to the twisted theory of the projective bundle. Okay, then you localize in the bundle directions. Okay, and when you do that, so yeah. Okay, let's try and get this right. So you will get. That's right. So the Euler class term that you had, which you were integrating against, will end up being the Euler class of when you localize. Now you're like, so you have your projective bundle, right? You localize your fixed dose like maps to X. Okay, this Euler class term will become the same Euler class term that cuts out like strata inside X. So it will become like the Euler class cutting out maps to DI. But then you have like a product of these, and so you end up cutting out the intersections of the DIs. Yeah, that's how it goes. Yeah.
In this one expects this to be true in higher genus. I mean, exactly as you said.
I think so. Yeah. Yeah. I mean, there's different approach. I mean, the proof. There's different approaches to. I mean, of course, the first step is you import it over to the Oberfeld side. And then you have to decide what to do next. Okay, so we like to put it in the bundle and then localize, but there's other ways to try and reduce it to the theories of the strata. So yeah, yeah.
So are there further questions?
Yeah, I have a question. Could I ask you a little bit more about the tropical interpretation of the obstruction to lifting? So like in particular, you're looking for sufficiently fine subdivisions of the tropical target, right? And so like earlier, Rahul was asking for maybe a more beautiful or geometric way to think about the things you're blowing up. Maybe I'm asking for the opposite. If I'm looking for a sufficiently fine subdivision, can I take something that's not minimal? Like, can I just subdivide like crazy? Can I just subdivide all of my original cones in my fan and end up with something which is sufficiently fine? Does that work, or is it do you end up with way too much?
So you need to guarantee that. So okay, let me make some space. So basically, let's just draw a few examples. So I'm just going to draw some tropical curves here. So I don't know, maybe I have something like this. I'm not in the toric world, so I'm not going to worry about these being balanced or not. And okay, fine. Maybe it does something else over here. And maybe there's other slopes. And what you do is you go through all the edges, okay, and for every edge you record the slope, okay. There's certain slopes you ignore. So for example, if you have a slope going off in this direction, which can happen, you just sort of ignore that. You only record the sort of positive, the ones that are in the positive orthant. And then the condition is that so you can take any subdivision you like, but it has to contain the rays with those slopes in. So I think if you do what you said, so I think if you keep let's think about this. Yeah, I think this is right. So I think if you just keep like blowing up, eventually you'll get all the rays that you need, I think, in this way. But there are more efficient ways to do it, just by sort of taking the weighted blow-ups and so on. Yeah, but it's not the case, of course, that, you know, so for example, let's say I need this ray here in the top left. Like if I just like start, you know, enjoying myself over here and going off to infinity, I'm never going to sort of transversalize things. I really, you know, you can do this as many times as you want over here. You still have got to go back and introduce this one. Yeah.
Okay, so let's thank Navid again for this talk. Thanks.